When it comes to Saturn, it's hard to put into words how fortunate humanity was to have the Cassini-Huygens mission. While 4 robotic probes have ventured into Saturn's domain, none have left a legacy quite like Cassini. Not only was it revolutionary, but it was also an artistic marvel, delivering mesmerizing data and awe-inspiring images that transformed how we view the ringed giant. From a scientific perspective, Cassini's mission was monumental. It served as the foundation for over 4,000 published research papers and helped uncover 6 previously unknown moons, along with new details about their chemical makeup. The probe endured nearly 20 years in space, traversing over 7 billion kilometers, including an astounding 13 years orbiting Saturn, sending back data on its gravity field, magnetic environment, atmosphere, and intricate ring system. Cassini was relentless. Even as it approached its final chapter, it continued gathering critical data right up to its dramatic demise. A dive into Saturn's thick mustard-colored clouds. This wasn't just an ending, it was a scientific crescendo, a planned plunge designed to protect potential life-harboring moons like Enceladus and Titan from contamination. But Cassini wasn't just a scientific marvel. It was a visual storyteller. The images it returned, from golden-hued storms to Titan's hazy atmosphere, are among the most iconic ever captured. These photos weren't just pretty pictures, they were snapshots of scientific breakthroughs in motion. Hosted today by Infinity Beyond, we begin our journey into this extraordinary mission with the first act, the grand finale. This phase marks Cassini's final months as it dove between Saturn and its rings, a feat never attempted before, to uncover secrets hidden for eons. Before this legendary dive, Cassini had already made waves. It wasn't the first to visit Saturn. That honor belongs to Pioneer 11 in 1979. But Cassini was the first to orbit it. And unlike fleeting flybys, Cassini became Saturn's companion, circling it 294 times and sending back over 600 gigabytes of scientific data. Even before arriving at Saturn, the mission was a marvel of engineering. Cassini was launched on October 15, 1997, aboard a Titan 44B rocket. Its destination, Saturn, the 6th planet from the Sun, and a world as enigmatic as it is beautiful. Reaching Saturn wasn't easy. It took 7 years and multiple gravitational slingshots, from Venus, Earth, and Jupiter, to finally reach its orbital destination in 2004. Along the way, Cassini carried a special passenger, the Huygens probe, named after Christian Huygens, who discovered Titan in 1655. This small lander would eventually separate from Cassini and descend through Titan's atmosphere, becoming the first probe to land on a moon in the outer solar system. Cassini's initial orbital insertion was a nerve-wracking moment. On June 30, 2004, mission controllers executed a precise burn to slow the spacecraft enough to be captured by Saturn's gravity. One mistake, and the spacecraft could have overshot Saturn entirely. A catastrophic failure. But the maneuver was flawless. Cassini slipped into Saturn's orbit, and history was made. What followed was nothing short of groundbreaking. Cassini mapped the magnetic field of Saturn with greater precision than any mission before it. It observed seasonal changes on the planet, tracked the complex interplay of its rings, and discovered dynamic weather patterns, including the now famous hexagon storm at the planet's North Pole. And the data kept pouring in. From geysers on Enceladus spewing water ice into space to the dense haze covering Titan, Cassini showed us that Saturn's moons weren't just rocks. They were dynamic worlds with complex geology and potential for life. But what made Cassini's mission so extraordinary wasn't just the volume of data. It was the creativity in its execution. The grand finale, the final series of daring orbits, wasn't part of the original plan. It was developed later in the mission's life as a bold way to collect data that no other spacecraft could. These maneuvers allowed Cassini to pass closer to Saturn's atmosphere and rings than ever before, skimming through previously uncharted zones. This first segment sets the tone for what will become one of the greatest interplanetary missions ever undertaken. Cassini wasn't just a spacecraft. It was a storyteller, an explorer, and a pioneer. Stay tuned as Infinity Beyond continues this breathtaking journey through Saturn's majestic realm. Cassini-Huygens didn't just arrive at Saturn overnight. It was the product of decades of planning and interplanetary coordination. And its journey to Saturn was a masterclass in gravitational physics and aerospace engineering. By the early 1980s, Voyager 1 and Voyager 2 had already been set on their respective paths to explore the outer solar system. It was too late to add a lander to those missions. Thus, the Cassini-Huygens mission was conceived, a purpose-built mission that would not only orbit Saturn, but also deliver a lander to its largest moon, Titan. On October 15, 1997, Cassini was launched aboard a Titan IV-4B rocket, embarking on a nearly 7-year voyage to reach its destination. But getting to Saturn wasn't just about aiming a rocket and firing. The spacecraft had to navigate a solar system dominated by the gravitational pull of the Sun, a force constantly trying to draw it back inward. To gain enough velocity to escape this pull and reach Saturn, mission planners devised a brilliant strategy: use gravitational assists, or slingshots, from other planets. Cassini flew by Venus twice, using its gravity to accelerate and redirect. After those flybys, it returned to Earth for a third assist, a bold maneuver that brought the spacecraft within just 1,100 kilometers, about 680 miles, of Earth's surface. From there, Earth's gravity launched Cassini toward Jupiter, its final assist before heading out to Saturn. This carefully choreographed planetary alignment, with the correct positions of Venus, Earth, and Jupiter, occurs only once every 600 years. In other words, the timing of Cassini's launch was absolutely critical. And it wasn't just the trajectory that was impressive. The spacecraft itself was a marvel. Cassini carried both the orbiter and the Huygens lander and was equipped with 12 different scientific instruments. These would eventually study everything from magnetic fields to surface chemistry, atmospheric conditions, and even seismic activity on Saturn's moons. Powering all of this was a trio of radioisotope thermoelectric generators, RTGs. Unlike solar panels, which are impractical so far from the Sun, RTGs use the heat generated from decaying plutonium-238 to produce electricity. It's a reliable power source, ideal for deep space missions where sunlight is scarce. This method of propulsion and power was not without controversy. Environmental groups voiced concerns about launching a spacecraft with radioactive materials aboard. But NASA and ESA assured the public that the spacecraft's design included multiple layers of protection, and the odds of failure were minimal. Fortunately, Cassini launched successfully and safely, and its RTGs performed flawlessly for the entirety of the mission. After its slingshot around Earth, Cassini approached Jupiter in December 2000. While the primary mission was Saturn, this flyby offered scientists a valuable bonus, a chance to test the spacecraft's instruments on a giant planet and fine-tune them before arriving at Saturn. Cassini provided stunning images of Jupiter's atmosphere, storms, and magnetosphere, along with new insights into its moons and radiation belts. This stopover was crucial. By the time Cassini left Jupiter's vicinity, it had traveled over 1.4 billion kilometers and was well on its way to the outer solar system. Every maneuver had to be executed with absolute precision. A miscalculation at any point could have sent the spacecraft careening into deep space, or worse, crashing into a planetary body. As Cassini continued toward Saturn, mission controllers on Earth performed course corrections and system checks. At every stage, the spacecraft transmitted data back to Earth through NASA's Deep Space Network. These communications had a round-trip delay of nearly 2 hours, a reminder of the incredible distances involved in interplanetary exploration. But even with all this planning and technology, the team still held their breath as Saturn approached. A successful entry into Saturn's orbit would require Cassini to fire its main engine for over 90 minutes. A critical burn to slow the spacecraft enough to be captured by the planet's gravity. Failure here would mean losing 2 decades of effort in an instant. Spoiler alert, they nailed it. Cassini's arrival at Saturn in 2004 wasn't just a triumph of engineering. It was a testament to human ingenuity, collaboration, and scientific curiosity. Every gravitational assist, every calculation, and every piece of hardware came together in perfect harmony to reach one of the most beautiful planets in our solar system. And this was only the beginning. In the next segment, we'll explore Cassini's early discoveries after entering Saturn's orbit, from the dazzling detail of its rings to the enigmatic moons that would soon change everything we thought we knew. Stay with us at Infinity Beyond as we continue this cosmic odyssey. Powering a spacecraft in the outer solar system is no easy feat. At Saturn's distance from the Sun, solar energy is too weak to be practical. That's why Cassini was equipped with something a bit more powerful and a lot more controversial: radioactive plutonium. Specifically, Cassini was powered by about 33 kilograms of plutonium-238, packed into radioisotope thermoelectric generators, or RTGs. These devices don't rely on combustion or fission like a nuclear reactor. Instead, they convert the heat released by radioactive decay directly into electricity. Even toward the end of its mission, Cassini's RTGs were still generating approximately 700 watts of power, enough to keep the spacecraft's systems running and its scientific instruments operational. The longevity of this power supply allowed Cassini to remain functional for over 20 years, including 13 years in Saturn's orbit. But carrying plutonium into space was not a decision made lightly. Had the launch gone wrong, or had Cassini re-entered Earth's atmosphere during its gravity assist without control, the consequences could have been dire. NASA ran worst-case scenario models and estimated that, if the plutonium dispersed globally, it might have caused around 5,000 cancer deaths, a projection based on long-term radiation exposure. That number was hypothetical and depended on a global dispersal that was highly unlikely. NASA concluded that the risk of such a disaster was about 1 in a million. And in the context of the potential scientific reward, the risk was deemed acceptable. Still, the public voiced concerns. Environmental advocacy groups challenged the launch and questioned the ethics of using radioactive materials in space exploration. NASA responded with transparency, detailing every safety measure and emphasizing that the plutonium was encased in protective layers designed to withstand high-velocity impacts and extreme heat. Fortunately, those safety precautions were never tested. Cassini launched flawlessly, soared past Venus and Earth, and began its journey towards Saturn, powered by a technology that had proven reliable on earlier missions like Voyager and Galileo. The RTGs weren't just powering basic systems. They supported a suite of advanced instruments, cameras, sensors, and communications. Every stunning image of Saturn's rings, every atmospheric analysis of Titan, every magnetic field reading, all of it was made possible by those glowing plutonium cores. In many ways, Cassini's power source was a symbol of the mission itself: daring, forward-thinking, and willing to push boundaries. And even at the end, the power was still flowing. Cassini didn't shut down because it ran out of energy. It ran out of fuel. Fuel, in this case, refers to the propellant used to adjust Cassini's position and orientation in space. Without it, the spacecraft couldn't change direction or stabilize itself to send data back to Earth. So, in 2017, when the last drops of propellant were nearly gone, NASA made a bold decision. Rather than let Cassini drift and potentially crash into one of Saturn's moons, especially those that might harbor life, the spacecraft would be sent into Saturn itself. This grand finale was both a dramatic end and a strategic one. It allowed Cassini to collect groundbreaking data as it plunged between Saturn and its rings, a region no spacecraft had entered before. These final orbits provided detailed information about the planet's atmosphere and gravity field, insights that would have been impossible to obtain otherwise. And so, the very source of Cassini's power, that little bit of plutonium, helped guide it from Earth, through space, into orbit, and finally, into the clouds of Saturn itself. In the next segment, we'll take a closer look at the instruments aboard Cassini, the high-tech tools that turned radioactive heat into revolutionary science. From infrared spectrometers to cosmic dust analyzers, we'll explore how Cassini became one of the most capable scientific machines ever launched. Stay curious and keep exploring with infinity beyond. As Cassini orbited Saturn and explored its many secrets, one of the mission's most groundbreaking components detached for a mission of its own. This was the Huygens probe, a lander developed by the European Space Agency, ESA, specifically designed to explore Titan, Saturn's largest moon. Titan had long intrigued scientists. Covered in thick, hazy clouds composed of hydrocarbons, it was a world of mystery. Beneath its atmosphere, some speculated there could be liquid lakes, methane rain, and even a subsurface ocean. But no one had ever seen Titan's surface up close, until Huygens. The probe itself was compact, only about 1.3 meters wide and weighing 300 kilograms. It was carried by Cassini for nearly 7 years before finally separating in December 2004. Once detached, Huygens drifted through space for 22 days before reaching Titan's atmosphere. At this stage, Huygens was essentially asleep. It was designed to conserve power until the moment truly mattered. A wake-up timer activated the probe just 15 minutes before atmospheric entry. And when it awoke, it was showtime. What followed was one of the most dramatic and scientifically rich descents in the history of space exploration. The descent through Titan's atmosphere lasted 2.5 hours. During this time, Huygens deployed multiple parachutes to slow its fall, beginning with a small pilot chute and progressing to a series of larger ones. This allowed the probe to remain stable and collect as much atmospheric data as possible during its descent. Its instruments sprang to life. Huygens measured the atmospheric pressure and temperature, wind speeds, and the composition of the gases surrounding it. For the first time, humanity had direct data from the atmosphere of a moon more than 1 billion kilometers away. But perhaps the most breathtaking moment came from its camera system. As Huygens descended, it captured images through the haze, gradually revealing a landscape that looked oddly Earth-like, complete with river-like channels, dark lake beds, and highlands. Yet instead of water, Titan's surface was likely shaped by liquid methane and ethane, flowing and evaporating much like water does on Earth. The probe didn't just float down, it landed. And not just any landing, a soft, successful touchdown on Titan's frozen terrain. The surface temperature was a frigid 179 degrees, 290 degrees, and yet the probe functioned for over an hour on the ground before losing contact. For the duration of its descent and surface operations, Huygens sent data back to Cassini, which then relayed it to Earth. The timing had to be perfect. Cassini had to be in the right position above Titan to receive the signals. A narrow communication window that worked flawlessly thanks to careful planning. In total, Huygens sent back 350 images and a wealth of atmospheric and surface data. It showed that Titan has a thick nitrogen-rich atmosphere, the only one of its kind among known moons, and that its surface features are shaped by seasonal changes and methane-based weather cycles. This descent, this one moment of contact, fundamentally changed how we see Titan. No longer just a blurry orange sphere in Cassini's images, Titan became a world, a real place with terrain, weather, and potential for astrobiological interest. Scientists now believe that under Titan's icy crust lies a global ocean of liquid water, kept warm by tidal forces and possibly containing the ingredients for life. The data from Huygens continues to influence future missions, including NASA's upcoming Dragonfly rotorcraft, which will explore Titan's surface in greater detail. Huygens was a triumph of international collaboration. While Cassini was led by NASA, the Huygens probe was built and operated by ESA, proving that space exploration transcends borders. Together, they achieved what no single agency could have done alone, landing on the most Earth-like world in the outer solar system. The legacy of Huygens is profound. It didn't just touch down, it touched human curiosity, scientific imagination, and our eternal quest to understand alien worlds. In the next segment, we'll return to Cassini and follow its continued exploration of Saturn's moons, from icy Enceladus to the chaotic surfaces of Mimas and Dione. These moons turned out to be far more dynamic than anyone expected. Stay with us at Infinity Beyond as we continue the cosmic journey. Before we move on to Cassini's final maneuvers, it's worth pausing to admire one of the most beautiful gifts this mission gave to humanity: its photography. Cassini wasn't just a spacecraft, it was a cosmic artist. Over its 13-year stay in Saturn's orbit, Cassini sent back more than 450,000 images. These weren't just scientific data points, they were visual masterpieces. They offered us an unprecedented view of the ringed planet, its iconic moons, and the rich complexity of its system. When scientists designed the Huygens probe, they believed it might land on a liquid surface, perhaps a methane or ethane ocean. That's how mysterious Titan was at the time. So the lander was engineered accordingly, with flotation capabilities just in case. But, as it turned out, Huygens landed on what's believed to be the dry bed of a lake. A frozen plain, etched with ancient runoff channels and shaped by winds that echo across Titan's distant surface. Meanwhile, back aboard Cassini, the spacecraft continued its dual role as explorer and documentarian. It captured Saturn in every lighting condition, from the planet basking in the glow of sunlight to rare alignments casting shadows across its famous rings. Saturn's moons, too, became stars of the mission. From Enceladus's icy geysers to the cratered face of Mimas, which resembles the Death Star, every celestial body in Saturn's orbit was examined and captured in crisp, often surreal imagery. Some of these images were even turned into breathtaking animations by mission enthusiasts and professional scientists alike. By carefully aligning, color-correcting, and sequencing Cassini's raw data, they created time-lapse journeys that simulate what it would feel like to ride on the spacecraft itself, watching moons rise and set, shadows drift across rings, and storms whirl beneath Saturn's golden clouds. And just to be clear, there's no CGI in these reconstructions. The images are real. The beauty is real. The only edits are enhancements in color and contrast to better reveal features invisible to the human eye. For instance, one iconic image shows Saturn backlit by the sun, a dramatic shot that casts the rings in silhouette and reveals faint outer structures never seen before. Another captures the moon Dione hovering over Saturn's atmospheric bands, a juxtaposition of icy rock and gas giant grandeur. Cassini's onboard camera systems, like the Imaging Science Subsystem, ISS, were among the most sophisticated ever sent into deep space. They worked tirelessly, not only snapping photos, but also helping with navigation, guiding the spacecraft as it maneuvered between moons and rings. And as Cassini's fuel reserves began to dwindle, scientists were determined to make every remaining moment count. They planned the mission's final act with precision, creating a phase known as the grand finale, a series of daring orbits that would take Cassini between the rings and the planet itself. This wasn't just for show. It was a calculated risk, designed to collect data never before accessible. And throughout this final dance with Saturn, Cassini kept taking photos, right up until the moment it plunged into the atmosphere, snapping farewell shots of the planet it had orbited for over a decade. These final images, the last glances of Saturn's upper atmosphere and the edges of its rings, carry a kind of poetic weight. They are the dying embers of a mission that pushed the boundaries of engineering and inspired a new generation of planetary scientists. Cassini's photography has influenced not only space science, but also art, education, and culture. Its images have appeared on classroom walls, in textbooks, at museums, in documentaries, and even on album covers. In a time where space can sometimes feel distant or abstract, Cassini made it feel intimate. It made Saturn's system tangible, and it did it one frame at a time. In the next segment, we'll dive into the grand finale, the final series of risky orbits that took Cassini closer to Saturn than ever before, revealing data that changed our understanding of the planet's internal structure, gravity, and rings. Keep your eyes open and your mind wide. The journey continues with infinity beyond. As the Cassini mission neared its final chapter, the team at NASA knew it had one last chance to unlock Saturn's secrets. With fuel reserves running low, a bold plan was set in motion, one that would take the spacecraft closer to Saturn than ever before, through uncharted territory between the planet and its rings. This extraordinary phase began on November 30th, 2016, when Cassini started a series of high-flying maneuvers over Saturn's North Pole. After each ascent, it would dive down toward the narrow F-ring, the outermost edge of Saturn's main ring system. Over the next few months, Cassini completed 20 of these daring orbits. These passes allowed scientists to study the outer ring regions and upper atmosphere with unprecedented detail. But this was only the prelude. On April 22, 2017, Cassini executed a critical maneuver, leaping over Saturn's main rings and into the narrow gap between the planet and its innermost ring. This marked the beginning of what would be known as the Cassini Grand Finale. The spacecraft embarked on a final sequence of 22 tight, looping orbits, threading the needle between Saturn's atmosphere and its innermost D-ring. This region had never been explored by any spacecraft. It was risky, thrilling, and scientifically irresistible. Each dive brought Cassini within just 1,600 kilometers of Saturn's cloud tops, closer than any spacecraft had ever dared to fly. At those altitudes, the spacecraft experienced increasing gravitational tug, radiation exposure, and the possibility of collisions with unseen ring particles. But the rewards were immense. Cassini's instruments measured the mass of the rings, the composition of Saturn's upper atmosphere, and variations in its magnetic field. This helped scientists determine the true age of the rings and gather data on the planet's internal structure, data that had eluded astronomers for generations. NASA described the grand finale as a high-risk, high-reward maneuver, a chance to collect incredibly rich and valuable information that even the mission's original planners could scarcely have imagined. During this phase, Cassini became more than a spacecraft. It became a kamikaze explorer, diving repeatedly into danger, all for the sake of knowledge. It performed measurements no probe had ever attempted, capturing data in real time and relaying it across the vast gulf of space to Earth. The team adjusted its instruments to scan for dust particles, sample atmospheric composition, and track variations in gravitational pull as Cassini skimmed above the clouds. Even the radio antennas were used to detect the density of ring material by observing signal disruptions. And through it all, Cassini continued to photograph Saturn's rings and atmosphere in stunning detail. The images from this phase revealed new ringlets, vortex-like structures, and auroras dancing across the planet's poles. What made this phase even more poignant was the fact that Cassini was heading toward its inevitable end. With each pass, it edged closer to the day when it would plunge into Saturn's atmosphere and be incinerated, a noble death designed to protect potentially habitable moons like Encelada and Titan from contamination. The decision to sacrifice the spacecraft was not taken lightly, but it was essential. Had Cassini been left in an uncontrolled orbit, there was a slim but unacceptable risk that it could crash onto one of Saturn's moons. And since Cassini had not been sterilized to the level required for planetary protection, this posed a risk to future life detection missions. By ending the mission in Saturn's atmosphere, NASA ensured that Cassini would leave no biological trace. It was a poetic and scientifically responsible ending, a final embrace between a spacecraft and the world it had studied for more than a decade. As the grand finale continued, excitement built around the world. Scientists, space enthusiasts, and even casual observers watched in awe as Cassini's final days unfolded. In the next segment, we'll follow Cassini's final plunge, a descent into Saturn's atmosphere that marked both an end and a legacy. What did Cassini see? What final messages did it send? And how did it change our understanding of one of the solar system's most mysterious giants? Stay with Infinity Beyond as the story reaches its emotional and scientific climax. As Cassini entered the final orbits of its mission, its proximity to Saturn offered a scientific opportunity unmatched by any previous spacecraft. These daring passes weren't just about spectacle. They were designed to answer some of Saturn's most elusive mysteries. One of the biggest questions scientists hoped to answer during the grand finale was, what lies beneath Saturn's thick cloud tops? The planet's exact internal structure had long puzzled astronomers. Thanks to Cassini's close flybys and gravity measurements, researchers were able to detect tiny variations in the spacecraft's trajectory, subtle wobbles that revealed clues about the planet's density and composition. This data allowed scientists to refine their models of Saturn's interior. It helped them understand how materials are layered beneath the clouds, and how fast the planet's interior is spinning, something surprisingly difficult to determine because of Saturn's lack of a solid surface and its complex magnetic field. And speaking of magnetic fields, Cassini's instruments picked up fascinating readings here too. Unlike Earth's magnetic field, which tilts at an angle, Saturn's is almost perfectly aligned with its axis of rotation. That's unusual. So unusual, in fact, that it challenges current models of how magnetic fields are generated within planets. But it wasn't just the planet itself that was under scrutiny. Cassini's grand finale provided scientists with the most precise measurements yet of Saturn's rings, their mass, composition, and even their origin. As the spacecraft passed between the rings and the atmosphere, its particle detectors identified tiny ring particles, icy fragments being drawn into Saturn's upper atmosphere by its powerful magnetic field. This ring rain helped explain how the rings might gradually dissipate over millions of years, altering Saturn's appearance over cosmic time. Cassini's high-resolution cameras captured ultra-close images of ring features, sharp-edged ringlets, strange propeller-shaped gaps created by hidden moonlets, and wavy distortions that revealed how gravity shapes the ring system. Some of these structures had never been seen before. The rings themselves, once thought to be ancient remnants from Saturn's formation, now appeared to be relatively young, perhaps only a few 100 million years old. This raises an intriguing possibility. The rings may have formed during the time of the dinosaurs on Earth. Cassini's final data helped weigh the mass of the rings more accurately than ever before. That measurement, in turn, helped determine whether the rings formed early in Saturn's history or are more recent additions, possibly the remnants of a shattered moon or comet. But beyond the data, the grand finale offered something deeper: a better understanding of how giant planets form and evolve, not just in our solar system, but across the galaxy. The dynamics observed in Saturn's rings, atmosphere, and magnetic field mirror processes that likely occur on exoplanets orbiting other stars. Cassini's last measurements even revealed icy particles being funneled into Saturn's atmosphere, material from the rings literally raining down into the planet, hinting at a dynamic interaction that slowly alters Saturn's composition and energy balance. In many ways, this phase of the mission became a cosmic autopsy, a deep scan of a planet in motion, revealing secrets that had remained hidden since Saturn's formation more than 4 billion years ago. And as the final orbit approached, there was one last mission left: to protect the potential for life elsewhere in Saturn's domain. Cassini's final descent wasn't just about gathering data. It was about planetary protection, making sure that Enceladus and Titan, two moons with the potential for life, would never be contaminated by Earth-based microbes hitching a ride on the aging spacecraft. By guiding Cassini into Saturn's atmosphere, NASA ensured the spacecraft would be vaporized. This act wasn't just scientific, it was ethical, a symbolic gesture of care for unknown ecosystems far from home. It's rare that a machine becomes part of humanity's emotional vocabulary. But Cassini did just that. It became a pioneer, a teacher, and ultimately, a guardian. In our next episode, we'll follow Cassini's final plunge, a graceful dive into Saturn's upper atmosphere, where it sent data until its very last heartbeat. What it revealed in its final moments still resonates today. Stay with infinity beyond as we approach the end of this celestial journey. Let's take a closer look at some of the final moments captured by Cassini during its bold grand finale phase. As Cassini approached its final days, NASA made a daring decision: trade the spacecraft's survival for a once-in-a-lifetime opportunity to get closer to Saturn than ever before. With fuel nearly gone, survival was no longer the goal. The priority became gathering every last bit of precious data. Cassini began diving through the dangerous gap between Saturn and its innermost ring, a region no spacecraft had ever entered. From this vantage point, it captured some of the most incredible sights of the entire mission. First were the shepherd moons, tiny satellites that help shape and stabilize Saturn's rings. One remarkable example is Atlas, a moon only 40 kilometers wide located near the outer edge of the A-ring. Cassini captured ultra-close images of Atlas, revealing an oddly smooth surface, virtually free of impact craters. Instead, the moon appeared to be covered in dust from the rings, forming a bizarre, disc-like shape that made it look like a flying saucer. But that wasn't the only incredible thing Cassini saw. The spacecraft also discovered tiny waves and ripples in the rings, caused by gravitational interactions with hidden moonlets. Some structures resembled propellers, created by objects disturbing the icy particles around them. This extreme close-up perspective allowed scientists to accurately measure the size of ring particles, from pebble-sized stones to ice chunks as large as trucks. Cassini's data helped determine the composition and evolution of the ring system. Meanwhile, Cassini's dust and plasma analyzers were still hard at work, collecting information on particle makeup and origin. It even confirmed a phenomenon known as ring rain, material from the rings slowly falling into Saturn's upper atmosphere, providing insight into how the rings may gradually disappear over millions of years. The spectacle was magnificent. Cassini was like a cosmic performer skating across Saturn's grand stage, capturing every icy arc before its final curtain call. In the next segment, we'll witness Cassini's last breath as it plunges into Saturn's atmosphere, sending its final signals home. It's a chapter full of emotion, science, and legacy, the unforgettable end of one of humanity's greatest space missions. Stay with Infinity Beyond, where the universe tells its story.